picking up some feedback? Am I picking up? Ah, there it is.
So I'm gonna start the stream just talking about what this project is and what I plan to do with it, why it exists. Um, I kind of went over some of that in the uh, intro video that I posted a few days ago. But this project is it's going to be a simulator for System C and using C++ and CMake and Conan. And what I plan to do with it is potentially use it for running performance architecture simulations. Maybe in the future, if it gets to sufficient level, maybe it could be used for things like firmware development and other aspects for that. The reason I'm creating this is partly because, I just for fun, I know System C moderately well, and I know C++ moderately well. I'd like to learn it, both of those, a fair amount better, and maybe get some input from a community. And I'd like to use it as a teaching tool. And yeah, let's go through some of the design goals. And I'm going to be learning some of these things like Markdown as we go. I don't exactly know the syntax, but this looks good to me. And I wonder if I do double dashes, will that get me? Nope. So let's look up a Markdown cheat sheet. This is fairly small. Let's check out, this is a neat web page called Learn X and Y Minutes. And it has many, many languages. I don't know if it has all of them, but it has a huge amount. And obviously it has Markdown. So here's what I want from Markdown. It has all the syntax for Markdown. And so we're using the headers. We can already see that here. Maybe I should make this a header 2. That seems reasonable. And we're looking for items. So we can do an ordered list and add sub items. That's fairly good. I don't see the same thing with an unordered list. So let's turn this into, actually, let's try this with sub items. Look at that. So we just had to change which thing we were using, which character we were using. So we're creating an SOC model. The SOC model is, instead of focusing on CPU core performance or GPU performance, I'd like to look at the interactions of all the different IPs that live on an SoC. So an SoC is a system on a chip. And we can take a look at a die shot here. This is an older SoC. but it's fairly representative of what the what an SoC is, right? We have our CPUs, we have a memory controller. This says DDR3 right here. Actually, it's probably the memory controller itself is probably in the North Bridge, and then this is the DDR3 physical interface, or we call it a PHY. And then we have our 4 CPU cores here, each with their own L2 cache. And then inside this large block are different IPs as well. We have a graphics array. That's the GPU. A display module, which takes the GPU data and converts it to whatever display protocol that we need it to convert to. Things like DVI, or, well, DVI is very old. DisplayPort, HDMI, those kinds of things. This multimedia engine is for encoding and decoding video, and then the I/O, that's for PCI Express and Ethernet and those kinds of things. And we can see the PHY for the display right here, the PHY for the PCI Express. And I believe this chip uses PCI Express to talk to the chipset, so they don't need a separate PHY for that. But I want to look at the interactions of how the CPU and graphics array and display and multimedia all talk to each other. And we want to make sure that they can all get the memory bandwidth that they need, and that we're not clogging up the chip somewhere. And so that's what I'd like to look at in comparison to something like Gem 5, which is a great simulator. It's open source and built by universities, and ARM and AMD use it internally, I believe. It's very core centric, and I don't necessarily want to be core centric. If it's possible, I'd like to figure out how to take the CPU core model and tack it on to this model, whatever we end up calling it. I'm calling the channel Dyson code, but I don't want to call the model Dyson code. So we'll call the simulator something, and hopefully we can have it interact with the Gem 5 core models and potentially the Gem 5 memory models, because as far as I can tell, those are fairly robust. And my gripe with Gem 5 is just that it's a little more difficult to make all of these different SoC interactions happen. And we're going to start with synthetic traffic, and then hopefully add in real traffic at some point. But we'll start with synthetic. And, if people have questions, make sure to ask in the comments, or, while I'm live streaming, you can ask in the chat. So let's take a look. This repo, like I said, it's going to be for all the code that we use on this YouTube channel. We're going to be creating the main project is going to be an SoC in approximately timed. SoC model. And we'll talk about what approximately timed means in just a few minutes. And the design goals that I have for this SoC model, like I said, I want to make it simple, which means it's simple to use and learn. I want it to be simple to extend. I want it to be simple to understand. And I want to be able to go through, or somebody to be able to go through the entirety of the code base and understand what's going on in each separate piece of code. I look at a lot of big projects, and especially open source, and you can tell, you know, maybe they merged two projects together and they look very different. They have different coding styles, or um, they the file structure is laid out in a much different ways, things like that. So I want to make this as consistent as possible. I have that actually in a bullet point of its own because I think it's that important. But if it's consistent, then it's going to be simpler to understand, easier to talk about. The modularity, it seems fairly natural to make the SOC modular. We have these different IPs, and IPs stands for intellectual property, but that's a kind of a terrible name for what they are. Module is, in my opinion, a little better. So I have a CPU here, and I have an L2 cache, and I can make those separate pieces of code and hook them up using System C and something called TLM that we'll talk about. It's fairly natural to split these models up into different modules. And we're going to be using libraries, C++ libraries, and then make it executable in its own module. And so I think it's a natural extension. We can use the object-oriented ideas of C++ and make these libraries and have consistent and easy to extend code. So I want to make sure the folder layout is similar. That's not going to be perfect. And I want each IP to, not necessarily each IP to live in its own repo or its own folder. Maybe I shouldn't put another subheader here or sub module or sub item here. So we'll figure that out. None of these rules are going to be set in stone, but we're not necessarily going to play fast and loose with the rules. So I want to try to keep things as consistent as possible. And my third major design goal with this is to use it as a teaching tool. I'd like to teach how SOCs are designed. How are the CPUs designed? And this is not just SOCs. This translates to pretty much any ASIC. They're designed fairly similarly. And I want to I want to use this to teach myself similarly. I've built System C modules, but I've never done something like this from scratch entirely by myself. So that will be a learning experience as well. I want to teach System C and C++. That's here in the channel goals as well. And I think it's fine to keep both of those. So teaching C++ and System C. System C is actually a library for C++. And I think it gets lumped in often with System Verilog or VHDL as one of the big three hardware description languages for designing hardware. We're not going to be using any of the synthesizable code here. We're going to make a higher level model than that. And System C is often seen as its own thing, but it's not its own thing. It is entirely built in and around C++, and it is just a library, so we can use it like any other library, like Boost, or another library that we'll be using in this simulator will be gtest. So it is fairly similar. A subset of System C is called TLM, or transaction level modeling. So that's what we're going to be using primarily. A transaction level modeling means we're taking each transaction, say the CPU sends a read request, and we're going to follow it through the SoC out to memory and back. And that's how we're going to model our SoC. And we're going to use a specific class, a TLM generic payload, to model those communications across the network. And this is different from RTL. We're not going to use wires, and we're not going to use a clock to model everything. There will be some notion of time, but we're not going to make sure that something happens on a rising or falling edge. And we may not model every single CPU cycle. So if nothing is happening for 10 nanoseconds, there's no reason we should go through each module and see, do you have something to do? And instead, we're just going to say, nothing has anything to do for the next 10 nanoseconds, and then we will pick back up. So that's kind of a high-level overview of TLM. Another channel goal that I have is to highlight current research. I'd like to find PhD candidates and other people that might want to talk about their research, and I might just go through and see what papers I can find on Archive or something like that, and see what's beyond state of the art. And I'd also like to learn from the community. I'm sure that there are people out there that knows different things better than I do. One thing I'd like to learn from the community is maybe GitHub Actions or some continuous integration, continuous deployment kinds of things. And, I would like people to make pull requests and to make comments on the YouTube videos and elsewhere so that we can make something that's really cool and usable for real workloads. And I want to make sure that we keep the community friendly. That's pretty key for me as well. And I'm going to commit these changes to the main branch. We'll just call it update readme. And that's okay. All right, so there's our readme. And then the next thing I'd like to do is kind of go through the code fairly quickly, and then we're going to create an AXI injector or AXI injector, and maybe a loopback if we have time. We can see here that I have an example module in my GitHub repo. This is the base directory. I have a README. You can see it right here. I'm using the MIT license. I'd like to get some feedback if that's a good license to use. I want to make sure that companies, if they care to use this, can use this without any um, burden, and without needing to share their IP secrets. I have one external dependency that I'm working on getting Conanized, but I'm having a little bit of trouble. So uh, if I'm able to find somebody that knows Conan fairly well, then maybe we will get that set up. And we can see we have one example module here. This example module is going to be used as kind of a skeleton, or this has the boilerplate code that I'm going to need to write for pretty much any other module. And so we can use this as a reference, and copy and paste is often considered bad, but we're going to do some copy paste of this example module and then tailor it to our specific needs. So why don't we dive into the code? So I've opened CLine here, and CLine is a really nice C and C++ integrated development environment, or IDE. It does cost money. I think it's something like $140 a year, so it's not exactly cheap, although I think there are you can either get it discounted or for free if you're a student, or if you're working on an open source project. So there is a potential that if you work on this project, that maybe you could get it for free. I honestly don't know exactly how that works. I don't particularly care for myself. I just bought it so that I could have it and use it. So we can see in here, I have a build folder, although I think I removed that build folder. I thought I did. There we go. The CMake build debug, which is where CLion makes its intermittent builds. I have an include directory. In that include directory is our example module.h. So this will be what gets included when we use the library. I have a source folder, and that has our CMake list and an example module. This just adds a library. It includes our includes a directory, and links it to whatever libraries that we need. And right now we're linking only to System C. That's the only library that we need at this moment. Although my assumption is we will probably need something like Magic Enum or another library at some point in the future, and we will add it here. And then it gets its package version from the Conan file. I have a test directory, so I want to make sure that we do unit testing. I'm going to try to do test-driven development, and there are two different types of tests that I think a lot of people associate with System C, with hardware development. So we're going to be doing unit testing. This is a software concept where we essentially take one class, instantiate it, and test that object, poke it, and make it do certain things. And so we can see here, I have an example module test, and I'm extending from System C fixture, which it itself extends from the Google test class. And we instantiate our module, and this is just checking, can we instantiate it? I have an advanced simulation time. This comes from that external dependency that I was talking about, the TLM2 test bench code that I'm using. And this just goes through and adds time. It doesn't actually do very much testing. We just can confirm it through the console, and I'll show that in just a second. And then I have another test. I just call a function, and then it returns 42, and I check to make sure that it returns 42. And we can hit play, and in here we can see hello from event handler at 2 nanoseconds. So this came from this advanced simulation time. I wanted to make sure that it was not happening here in this can instantiate. So this isn't the best way to do unit testing. So we will want to make sure that things get called automatically rather than inspecting the console to see that some output happened. This was just a quick example to show what we need to get an exam, something running and advancing time. So my next step here is to actually take this example module, and I'm going to close CLion here and go to my console, and I'm going to copy the example module, and I'm going to call the resulting thing AXI modules. And actually, before we do that, I'm going to go into the example module here, and I'm going to remove the CMake build debug because we don't need that in our new module. And there might be a way in CP or maybe rsync to exclude directories. I don't particularly care. I don't need that build directory to live in the example module forever, so I can get rid of it. So I'm going to copy the example module to AXI modules. And this AXI modules, what it is going to be will be two kind of bare bones. One will be an injector and one will be a loopback, and those can be used for unit testing. And we can take a quick look at the AXI specification, and maybe I have a diagram. Here we go. Here's a diagram of what we will be making. So we may make 3 modules, we may make just 2. So we will have an AXI manager. This will be an injector, and it will inject read and write requests and things like that. And those will go over the AXI bus, and which we are modeling with TLM, to an AXI subordinate. And so we are definitely going to make this blue box. We are definitely going to be making the green box, and we may hook them up, or we will be hooking them up together. There is a possibility we could make this multicolored box. This would be kind of like a something that lives in between. And so we're going to define some things. We're looking at the forward path. The forward path goes from the AXI manager down to the AXI subordinate. You can think of it as going from core to memory, and memory would be the endpoint. And then the backward path is going to be essentially just backwards from that. We're starting at memory or the AXI subordinate and going back to the manager. So we're going to create 2 small modules that run the AXI protocol that we can use for continuous integration and continuous development, CI/CD tool chains. And when we start creating more interesting AXI modules, then we can use our injector to test subordinates, and we can use our loopback to test our managers. So I'm going to be using the term injector and manager kind of interchangeably, and subordinate and loopback sort of interchangeably. The reason I'm calling this an injector is because we're going to create traffic and inject it into the network. The reason I'm calling this a loopback is because we are going to receive traffic. We're going to receive a read request or whatever it is, and very quickly get it back on the network. So, as soon as the clocking rules will let us, we will return our, say, read data. If we get a read request in, maybe we'll just say it takes one cycle to get a read request back. And so we'll wait one cycle to start sending our read response. And, when we start modeling memory, that won't be the case. Memory will take multiple cycles, sometimes hundreds of cycles, to return read responses. And we will want to model that. But for now, we just want kind of a loopback so we can do some quick testing and not have to worry about what the intricacies of subordinates are. And similarly, we want to have an injector so we don't have to worry about the intricacies of, say, a CPU model or a GPU model that would be very detailed. We just want to inject synthetic traffic, see it go through the system, and see it come back. So that's the AXI protocol. This document is an overview of the AXI specification. I don't think it is complete, but it is good enough for us to work from. And you can just search for AXI spec and find it. I think that's all I did. Another specification that we may do on this channel is CXL. I know that one actually a fair amount better, but AXI is used more often for kind of smaller projects. These slides are describing TLM, transaction level modeling. So we have our initiator and our target, and this would be our manager, and the target would be our subordinate. And we create a payload and send it to the target and then receive a response back. And you can see the timing points. We begin our request. We receive an acknowledgement that the request has been received. And then we send a response back. And then we send an acknowledgement that we received the response. And you can see, this interconnect here would be that multicolored box. So we have our manager, interconnect, and subordinate. One thing that I want to kind of touch on again, so RTL is going to be pin accurate. That means we are modeling wires, we are modeling pins from one module to another. And we're not going to be doing that. We just have one function that takes care of all that information for us. So we are definitely abstracting away a lot of the low-level details. We don't care about them. And that comes from simulation speed. We can see here, if we're simulating every event, that's 100 to 10,000 times slower. I don't know about these numbers. It could be even faster. RTL simulations, especially at the SoC level, can be very slow. Sometimes taking a day or multiple days to run through an entire SoC simulation. So let's get back to our code. Oh, I forgot it. So here we can see we have our AXI modules, and we're going to start running CLion here. Actually, yeah, this is fine. We're going to trust the project. and we're going to run Conan. And then we'll run CMake and ensure that everything is building. So we can see that CTest and example module are available for building. Example module will not run anything. It doesn't have a main function, but example module test does. So we can run example module test and ensure that everything is working after we did our big copy. So now we can do some refactoring. And I'm going to change this class name. So we're going to start with an AXI injector. And so we'll refactor. Shift F6 is the command, but I may use the mouse a lot more just to be more illustrative, but I'm not sure. So we're going to do AXI injector. And so the nice thing is it will change the constructor name here. And I think in source, changed it from example module to AXI injector. So the next thing we're going to do is rename example module.h to AXI injector.h. And this might break because I don't believe this will pick up the change. Oh, it did pick up the change. Okay. Oh, it didn't run the refactor. So we can see with the red squigglies that it can't find AXI injector.h. Actually, I don't want to call this AXI injector. I want to call this AXI modules because we're going to put injector and loop back in here. And we may put in an interconnect in here as well. So we're going to do this refactor, and we're going to change this to AXI modules. And let's go into our test code and make sure that that happened. Oh, I want to change this to a library include. Excellent. And we can build. And actually we can do more than build. We can run our tests. So let's change our namespace. And again, that is, we're going to do a refactor. Refactoring means we are changing the code without changing the functionality of the code. And we call this, should we just call it AXI? I think that's reasonable. If we run into a lot of collisions, maybe we will change that later. But for now, AXI is concise and descriptive. And we can see using namespace AXI, so that's great. We should have similarly AXI injector. Excellent. And in the test, I think I'm going to put in using namespace AXI. So that will make our code a little easier to read. And let's just run our unit tests another time to make sure that everything is working as we expect. We're going to rename example module test to AXI injector test. Inject test. And you can see it changed it in each of the test fixtures. we should be good there. And now we're just going to start changing our CMake list. So this project is no longer called example modules or module. It's called AXI modules. And let's get rid of this dead code. I don't actually need it. We need gtest and system C language. So right now we're just going to essentially find every reference to example module and change it to AXI modules. And you can see that refactor automatically did that for us in the includes, which is nice. And we'll reload the changes. And yep, that's it's not finding the new the new library. So we'll change this to AXI modules. And I'm seeing here that we need to change this from example module.cpp. There we go. So before we get the test, let's get the test running. So we can see that example module is what we're referring to in the test, but we actually want AXI modules. And so this should resolve things for us. And there we go, we can run our tests. I noticed I forgot to change the name here from example module to AXI modules, or AXI injector. So let's do that refactor. And I believe that should have changed it in the source. Yeah, so it changed it here as well. We'll reload that change and we can run our unit test just to make sure. That's the nice thing about the unit testing infrastructure is we can make all of these changes and ensure that we're not changing functionality. I do want to change this to AXI injector test, because we will have at some point an AXI loopback test. And we'll reload the changes here and AXI injector test. Excellent. And now we can start doing interesting things with our AXI injector. So our AXI injector is inheriting from SC core SC module, which means we can have an SC method, and we are using events. So this is an event-driven simulator. And you can see I have an SC event E. I should probably rename that to event. E is not super descriptive. And maybe we'll change this to forward event or backward event if we need multiple events. So SC events you can only set one event. So anytime you notify the event, it will discard anything that it received earlier. So you need to be a little careful with them. But it's not a bad thing. I like having just one event, and then we will schedule more events as we need them, or schedule future events when we get to the future. So we're kind of putting off event scheduling as far as possible. We don't need this something. I'm going to keep event handler because I think we will use it at some point. And here we have our start of simulation, and that is just notifying the event to happen 2 nanoseconds later. We can see in the constructor of our AXI injector, which I might move up a little bit, we have to have this special macro sc has process. So we just register our process with systemc, and we register this sc method with systemc, which essentially just says this event handler exists and it is sensitive to the event. So whenever event.notify gets called, it will know that, after this amount of time has passed, that it will after this amount of time has passed, it will call event handler. An event handler is required to be a void returning function and not take any arguments. So we will need to figure out, once we get into the event handler, what we're actually supposed to be doing. That will not be extremely straightforward every time, but generally is pretty straightforward, because we will have some sort of FIFO or some other structure that will say, this is the thing that's happening next. Maybe we get a bunch of read requests and we need to respond to those read requests in order. So that's what we do. We just take it off the FIFO, or maybe we have a stack, so we take it off the top of the stack. So whatever it is, it's usually straightforward to figure out what we need to do during that clock cycle. So here I'm going to move this constructor up just because I like it up at the top better. And we'll save. This don't initialize is kind of a funny thing. It just seems like it's hanging out here doing nothing. But, you'll notice that when I run injector test, since I got rid of this function, we need to get rid of the test as well. That hello from event handler only gets called once. If we comment out don't initialize and we run this again, I expect that it will get called 3 times. Oh, it only got called twice. Actually, that sort of makes sense. So you'll notice that it got called at 0 seconds and at 2 nanoseconds. So during construction time, or maybe during start of simulation time, not during construction time, the event will just get called. So all events happen at time 0, unless you specifically say don't initialize this, don't run this at time 0, which we don't want to run it at time 0. We don't have any work to do at time 0 in general. So there are some times that we may want to have it run at time 0. I generally use the start of simulation as my way to kick off events instead of just relying on the event to just happen. Okay, so right now we have some fairly basic tests, and I'm going to change this from example and E. That's why E is not a good name for the event. I used it again for the example. So I'm going to pass in the name test AXI injector. This name for unit testing doesn't matter. It will matter when we start printing out statistics and doing debug and things like that. But at this moment, it does not matter. So let's make sure that everything works. And then I'm going to add this to our GitHub repo. One other thing that I didn't go through. So I went through CMake lists, but I didn't go through the Conan file, which I'm glad I remembered that. So we're gonna do AXI modules. And we have our name here. Oh, it already, the refactoring found that name and changed it. And we're going to change this from lib example modules to lib AXI modules. And let's rerun Conan and make sure that this worked. There is some work we'll need to do. We'll need to, change this build to a more meaningful name. We'll look into that probably in a future stream. I don't think we'll get to that today. And we'll run CMake. So we run Conan, we'll rerun CMake, and then rerun our unit tests. And now I will add this to our GitHub repo. Let's check what branch we're on. I think we're on main. So I don't want to put this on main yet. So we're gonna check out a different branch. So we're gonna do a git checkout -b that says we're gonna go to a new branch, and we'll call this create AXI modules. And I'm going to do a quick grep for example in the AXI modules and see if I missed something. I missed it in the README. Here we can see in the Ninja log that it's still there. I don't care that it's in the CMake build directory. We can get rid of the CMake build directory and those will go away. But I don't particularly care. CMake build will not get included because I have it in my git ignore. Yeah, let's change the README while we're here. We'll say AXI modules. Let's close this so we have a larger palette to work with. So this folder has primitive AXI modules for development. And CI, CD. And now we can commit our AXI modules folder. So we're going to do a git add. We can do a git status just to make sure that that got added. And I want to make sure that CMake build debug didn't get added, which it doesn't look like it. That's good. So here are all of our new files. I did do one change to the README here that I'm not going to add that to this commit because it's a separate thing, and we'll try to keep each pull request to be one overarching theme. And so let's do a git commit, and it'll bring up Vim, so we can say we're adding AXI injector and AXI modules folder. And then we'll push. And because we're adding a new branch, we get this nice little helpful command line. And I'm just going to copy and paste it. And there it is. and it gives us a link. We can create a new AXI or create a new pull request from this link, but as of right now, I don't want to do a pull request, and I just see that this has a typo, and we'll put that in the next we'll just push that now. And when we do the pull request, we will squash all of these commits together into one big overarching commit. So this branch, right now, it has a bunch of commits, including this very tiny fixing a typo in README. Oh, I accidentally added the other README. That's okay. It's really not that big of a deal. I do want to try to keep things as one, overarching theme, but it's not, that particular change is not that big of a deal. Okay, so now that we have committed everything, we've made sure that everything works. We can pretty much close all the CMake lists, and we're going to work with three different files. We're going to work with the header, the CPP file, and the test file. And one way that I often work is I have my production code sitting on the left and my unit test code sitting on the right. And so because this is a forward NB transport forward module, the injector is going towards memory. It's not responding as memory. We're going to put in a simple target socket, actually. But I don't remember the syntax that we need for simple target socket, the event. So we're going to cheat, and we're going to inherit from what did I do? There we go. We're going to cheat and inherit from this interface for a moment, and we can generate the function that we need. So we need this NB transport forward function, and so that looks good to me. And now I'm going to get rid of this this inheritance. Get rid of this override, and we'll call these better names. So one thing that this does is it puts the ampersand for passing by reference in next to the name, which is arguable whether that's correct. So I'm going to actually put it next to the type, because I am very specifically saying that this type is a reference TLM generic payload. And similarly, it's a reference TLM phase. And I'm going to call this time. And actually, we will probably not use this time variable at all, but we need it to conform to the TLM interface. And I'm actually going to get rid of this, and we'll regenerate it. Actually, let's grab body. So here we have our NB transport forward function. It says it's never used. That is correct. We will get it used. I did break a rule. I just realized I started writing production code before I wrote a unit test. So let's write a unit test. And one thing that we will need in this unit test is a handle to a socket. So we're going to do auto socket equal AXI injector. Oh, what did I call it? Injector. Get socket. So we don't have that yet. That's okay. We'll create a new function. Let's call it void for right now because I don't recall the exact type of that socket. I should have done it. Generate in place. That's okay. Oh, I added a curly brace that didn't need to be there. Okay, so I'm gonna add a socket. TLM utils, simple initiator socket. And this is a templated argument. And the template that it takes is the type of the module that we're using. And we'll just call this socket. So this works for me. And we can call this auto return socket. Do auto reference. Cool. Okay, this is giving us squigglies. Great. It is no longer. One thing that I need to change, I realize I don't necessarily like always seeing these helpers in here. Sometimes that's really useful. Sometimes it just gets in the way. I might change that offline. And if people want to see that action, I can do it online. I just got to figure out how to do it. It's somewhere in the settings. I don't quite remember where. And so we're going to get the socket, and on that socket, we're going to call NB transport backwards, actually. I need to think about what we need to call. So we don't need the socket here. I realize that we're jumping ahead. I think it's okay to have this get socket code. And we will just say, or ensure that the socket exists at this moment. I'm not going to test anything beyond that. So let's make sure this test functions. Unused variable, that's okay. Now, do I want to bypass that, or do I want to just use the variable? I think for now, I'm just going to turn off the warnings. So right now, all warnings are treated as errors, and this should get us past that for the moment. Oh, binding failed. That's okay. Perfect. So that's actually more helpful than not used variable. So in the we actually need to, this needs to be called backwards. This is a place that I think a lot of people get tripped up, and I actually got tripped up on this a lot. So I just implemented the forward interface because we are using an injector. So we are going forward. The problem is that, or the disconnect is that we're actually instantiating something that will take a backwards interface. So we need to instantiate backwards. So on the return path, this will on the return path, this will get called. So we are going to call on the socket and be transport forward as we're going towards memory. And then we will receive something, and something else will call on the socket and be transport backwards. And that's when we will do something inside of this module. So we need to change this from simple initiator socket to simple target socket. Is it target? I thought it was target socket. Oh, I'm importing the wrong thing. Simple target socket. And so now this should find it. Excellent. And so we are going to, in the constructor, say what should get called when we when NB transport backwards gets called. Register NB transport forward. Maybe I do have this incorrect. I'll have to think about that for a second. Because I don't think we're registering NB transport forward. We should register NB transport backward. Comment this out and make sure that so we're not actually working with this test, we're working with this one. NB transport forward. So it still wants register NB transport forward. Simple. Oh, I do want simple initiator socket. And now we should be able to register and be transport backward. And this should just take our function and be transport backward as a pointer. I don't recall. Oh, we need to pass this and MB transport backward. Let's try this again. Maybe this will tell us what we need. So we need to pass this, I'm sure of that. And we should be passing this function. So that's not working, and I don't recall why. Oh, this is a class. So we can look in the header file. Sometimes I like just finding the code. It'd be great if there were a Stack Overflow suggestion here. Okay, so let's look at the header file really quick. So we need to pass in a module and have a function pointer here. I need to put the function, or put the class name. And I believe why is that not functioning? Reference to a non-static member function. That but we can do this a different way that I know a little better. I don't know the simple target sockets incredibly well, or the simple initiator sockets. I don't. I don't use it very often. I've generally inherited. So let's do that. Let's inherit from the Okay, so we can just have an initiator socket here. We have our NB transport backward. We're inheriting from the TLM backwards non-blocking transport interface. And then in the constructor, we're just going to call socket.bind, and we're going to bind to this class. Backwards interface. Oh, we need a reference. So we need to dereference this. We are a non-blocking transport interface. What are we missing? No function to implement because we have the correct functions. Maybe we don't need to bind. Let's try this. Yeah, port not bound. Maybe the problem is we just need to bind it to something. So we'll need to make a mock backwards interface. And so we're going to include gmock. Include gmock.h. And we're going to have our mock forward interface. And we're going to publicly, oh, I forgot class. Publicly inherit from TLM utils oh no, it's just in TLM forward non-blocking. And then we're going to generate our functions that we need. And we're going to use gmock. And the way that gmock works, it's a mock function. Mock method. And we need to put in the return type, the name, a list of arguments, and then a list here. Excellent. So we can bind to this. So we should be able to do injector get socket dot bind. We'll need to make a And this does not work, which is fine because we need to add a socket here. This is going to be a target socket. And we'll need a constructor here because we need to find this socket here. This is weird to me. I'm not sure why it's not letting me find. I think we're adding a little too much code for the moment. So I think what I'm going to do is remove this for now. We'll come back to it. And we'll get rid of our socket code and just test the NB transport backward function. Because we can test this without a real, without binding the sockets. So I should have done this earlier. And so we can create a TLM payload. We'll call it payload. TLM phase, and then SC core, SC time. And so we're just going to pass in payload phase and time. And I think this should function. We're not doing anything. Port not bound. I forgot to remove the port from here. And I'll do some searching offline to figure out what I was doing wrong there. Cool. And we can do an expect equal. We'll make it fail. So you'll notice that I'm just trying to make it fail to make sure that this test is doing something. So I'm returning TLM completed, and then I'm returning TLM completed, but I'm expecting to see TLM accepted. I just want to see that this test fails before I assume that it works, and it did. So we expected TLM accepted, which is 0. This is just an enum, and not an enum class. It's the older style enum. So now we can change this to be TLM completed and see that it works. And this gets us to a point when we have a functioning NB transport backward method that does nothing, essentially, which is fine for the moment. And then we will need to create our sockets. And like I said, I'll do some research offline to see what I was doing incorrectly there. So I know earlier I was having trouble explaining because I trip up on this as well. The forward and backward interface. So when uh, when we're going forward, we're going from the injector to the loopback. We call on the socket, we call NB transport forward. And that is the injector calling a function inside the loopback. And then when we get to the end, we're going to have the loopback call a function inside of the injector, and that is NB transport forward. So we have a socket on either side. There's a socket in the injector and a socket in the loopback. When we make any call, we call NB transport forward from the injector on that socket. It's a member function, not a static function. So we call it NB transport forward, and then we call it NB transport backward from the loopback, and we call that on the sockets themselves. So we need to create NB transport backward in the injector, and similarly, we will need to create NB transport forward in the loopback. Losing my train of thought. Hour and a half of streaming is not super conducive to quick thinking. And so we're at a fairly good place right now with the injector, except for the socket issue. And we can, offline, or I guess maybe online, we can make our loopback. So let's just do that right now. I don't know why I'm doing this in the terminal. I find it easier. So we will copy AXI injector. And we're going to call it AXI loopback.h. Source. We'll have AXI injector, and then we're going to call it AXI loopback.cpp. And similarly, we're going to have AXI injector test, and we're going to call it AXI loopback test. And let's open each of those files and make sure they say loopback. This one will target socket and NB transport forward. And I haven't included these yet, so that's why I can't really do the refactoring, but it's fairly quick to do it manually. Okay, so now we can start adding things. So AXI loopback test.cpp. We'll add it here as well. Now I realize I'm adding a library and I call it AXI modules, so I will want to have both in there. So let's change this. Just put AXI loopback.cpp, and we can get rid of this. So let's reload our CMake and build. AXI injector test works. AXI loopback test, hopefully that works as well. Yeah. So let's go into AXI loopback test and make it fail. To ensure that it's doing something, and it sure is. And now we can add this to our Git repo. Let's take a look, Git status. So we've modified the CMake list, we've modified the injector. I realize I want to commit these 3 files before we commit the loopback. And so we're going to say to the injector, we MB transport backwards function. And then we're gonna now look again. We have our CMake list that we've modified for the loopback. We're gonna add these 3 files. And then we're gonna do a git commit-a and make sure we have our CMake lists and all of those files. And I'm going to say add AXI loopback. And I think that's a good place to quit for the day. I'm going to push this to the branch, and if anybody wants to look at the branch, they certainly can. And for those who joined, thanks a lot. For those who are going to watch this later, thanks. And I will post this as a video on demand, and similarly do a summary video. But that's all for today. Thanks a lot. Oh, actually, I realized I wanted to go through one more thing. I don't have it open. That's okay. I have it here. There we go. So this is one of my favorite papers. You can do a quick Google search for it and find it. It is behind a paywall, so I don't necessarily want to share this illicitly. I don't really know the ideas behind that, but we're going to look at 2 different things in this repo. But this this diagram here is really neat to me. It kind of it illustrates the layers of transformation, or the levels of transformation of trying to take a problem and get electrons to do work and solve that problem. So computer science lives up here, we're writing programs, and actually our simulator lives up in um, these top four levels, right? We have a problem where we want to run a simulation and uh, determine, what kind of architectural trade-offs we want to make, and so that's our problem. So we're translating that to an algorithm, um, and a program. This algorithm and program are happening simultaneously. We're doing that through test-driven development and just through creating the simulator. And then our program gets compiled uh, to corresponding machine code, which uh, gets run, or is defined by the instruction set architecture. So we live in this area, and then what we are modeling happens to fit inside of these two, the ISA and microarchitecture. ISA stands for instruction set architecture, and the instruction set architecture is all of the um, assembly language and machine code that is visible to the user. Um, it's all of the registers, the visible registers, uh, you know, with things like out of order execution. Those registers are not always, or every single register is not viewable um, by the software, by the operating system. So, the advertised registers live in the ISA, and other things, things like the call stack are determined by the operating system and the ISA together. What we're looking at in a lot of respects is the microarchitecture. So things that are not visible to the operating system, to the programs that use our SoC. And so that's a lot of what we're modeling. Caches live here. If I'll have to think about what else lives in the microarchitecture. I don't have that off the top of my head. But it's how you implement a chip to get to the ISA. How do we conform to this ISA with circuits? And this ISA is kind of that in between level. So everything is pointing down. Everything on top of it is pointing down to the ISA, and everything below it is pointing up to the ISA. So we want electrons to do work. Well, we can put them into circuits, and we're using CMOS transistors to make these cool circuits. And we make AND gates, NAND gates, inverters, all of those kinds of things. And then we can take those NAND gates and NOR gates and things like that and make them into higher level functions like multiplexers and demuxes and lookup tables and RAM and ROM and all of those kinds of things. So those are the circuits that we can create, and then we make them into bigger blocks. Things like registers, things like the out of order execution unit, things like caches, and all of that stuff. And then we take those big blocks and put them together to create an SoC that conforms to an ISA. So this paper is really fun. It's a little dated. I think it's from 2001. And, right now it's talking about, a 1 gigahertz chip. And then I think it says, what if we get to a 10 gigahertz chip? And this is when clock speed scaling was expected to just continue. But we ran into a power wall with, Dennard scaling no longer being the case. When we go down in nodes, we no longer get a power boost or, reduced power. It used to be we could go down a node and increase clock frequency because that smaller node took less power. But instead, it takes about the same amount of power as we go to smaller and smaller nodes. Um, but yeah, we ran into a clock frequency wall, and we were stuck at 3 gigahertz for a really long time, and now we're in the 4 gigahertz and low 5 gigahertz for boosting, and so that's where we are at this moment, with multi-core. But a lot of the things that this paper talks about, oh, here's the 6 to 10 gigahertz clock frequencies. A lot of the things that this paper talks about still are relevant. This levels of transformation is still relevant to today's processors. So it's an easy read, but it's like I said, it's a fun read. And that's pretty much all I have for today. We'll go through and resolve our socket issue, and that will be what we'll work on next time. And then we can bind the loopback and the injector together in SC main and run some transactions. Hopefully that's what we'll get to on Friday. And I'll be streaming Mondays and Fridays, 11 to 1 Pacific time. I think I'm going to cut it a little bit early today, but I'll try to do 11 to 1. So thanks everyone for joining. I really appreciate it.